Now let us proceed to finding the maximum value of an objective function given constraints by graphing. Now the vertices or corners of the feasibility region are also known as the critical points. As you recall, the corner point theorem, also known as the fundamental theorem of linear programming, states that the maximum or minimum value of objective functions always takes place at the vertices or corners of the feasibility region. Now, this theorem reduces the number of possible maximizing or minimizing solution to a small set of points. We can just find the value that maximizes or minimizes by simply evaluating the objective function at each of the critical points. For instance, let us solve the following maximization problem graphically. We are to maximize this function here given by p of xy equal to 15x plus 6y. Subject to the following constraints: x plus y greater than or equal to 2, 2x plus y less than or equal to 8, and x plus 2y less than or equal to 8, and also x and y has to be greater than or equal to 0. We've solved this by first looking for the feasible region. So in our previous discussion, we have discussed how to find the feasible region. Suppose, for instance, we have performed all those steps and we're able to find there or identify that this is our feasible region. Then the next step is to identify the corner points or the vertices of the feasible region by identifying the points here. These are the intercepts, the y-intercepts. The y-intercept for this green line and the orange line, and this point here is the intersection of the blue line and the orange line. You can solve this by solving the system of linear equations, either by elimination or substitution method. And these 2 points here are the x-intercepts for the green and the blue lines respectively. So now after you have identified all those critical points, your next step is to evaluate your function. So the objective function, the objective function here, which is p of xy, will be evaluated at each of these points here. And then you compare the results. So you evaluate it at 0, 2, you get 12. Now if you evaluate p of xy at 0, 4, you get 24. You evaluate it at this point here, 8 over 3, you get 12. And then at the point 2, 0, you get 30. And at the point 4, 0, you get 60. You compare then the values. The one that has the highest value, which is this point here, 4, 0, that gives us the largest value for your p of xy. So that means that the maximum value for your objective function is equal to 60. Now let us solve the following maximization problem graphically. We want to maximize this function here, c of xy equal to 25x plus 15y, subject to the following constraints. So in order to solve this, we have to first identify our feasible region. We can do that by graphing first the line y plus or x plus y equal to 6, and then the line y is equal to 2x, and also the line x equal to 0 or the y-axis, and the line y equals 0 or the x-axis. And since they're both greater than 0, therefore that means that it is on the first quadrant. So for this one, you just have to know that these are all on the first quadrant. So that means that we are going to graph our line on the first quadrant. So we can graph this by getting representative points. So you can assign x and y values. So suppose this is your x, you solve for y. So we've solve, for instance, x, when x is 0, y is equal to 6. And then when y is 0, x is equal to 6. So these 2 points here. So you have 1, 2, 3, 4, 5, 6. So this is this point here. The other one is 1, 2, 3, 4, 5, 6. That point. And then you're just going to connect these 2 points here. Then let us graph the line y is equal to 2x. So for the line y equals to 2x, we get, again, representative point. We have x and y here. Now when x is equal to 0, y is 0. So it is this origin here. And then get another x value. Say, for instance, when x is equal to 1, y is equal to 2. So when x is equal to 1, y is equal to 2. So we're going to connect that line. All right, so these are the 2 lines here. This is this red line here is the line y is equal to 2x. And the blue line is the line x plus y equals 6. The next is to identify the feasible region. But before we identify the feasible region, let us first get the intersection point here. So we are going to solve this system of equation here by substitution method. So we do that by substituting y here by 2x, since y is equal to 2x. So we have x plus 2x is equal to 6. We have x plus 2x is 3x equal to 6. Divide both sides by 3. We have x equals 2. So if x is equal to 2, we have the x coordinate is 2. And then you plug it into the y here to get the y coordinate. So when x is equal to 2, y is equal to 2 times 2, which is equal to 4. So the intersection point in this case is the ordered pair 2, 4. So this is the ordered pair 2, 4. Then after that, we're going to label each region here and identify which one is our feasible region. So let's suppose this is a region 1, 2, 3, and 4. So let us examine first if region 1 is the feasible region. So we do that by getting a representative point. So we have region 1, for instance, and our representative or our test point, we'll just call that our test point. So the test point in this case will be, you just have to look at the point here. Now it should be before 2 because this is the intersection point. So you could have 1 and then let's say, for instance, 1, 1, 3. So our test point will be 1, 3. The ordered pair 1, 3. 1, 3. So if this is 1 and this is 3, this is the point 1, 3. That is the point 1, 3. Now let us check if this 1, 3 satisfies both of this inequality here. So if x is equal to 1, you have 1 plus the y is 3. So 3. 1 plus 3 less than or equal to 6. So 1 plus 3 is 4. That is 4. Is that less than or equal to 6? Yes. So first inequality is satisfied. What about the second inequality? Y is less than or equal to 2x. Our y is 3. So 3 less than or equal to 2 times 1. So is 3 less than 2? The answer is no. 3 is not less than 2. So therefore, 1, 3 is not satisfied on the second inequality here. So therefore, region 1 is not a feasible region. So you consider a different region. For instance, let us consider region 2. Region 2. So if you consider region 2, you look at a test point. What would be your test point here? Now for region 2, we can have a test point that is, you could have 2 less than, and then the y coordinate should be less than 4. So you could have a 2, 3 or a 2, 2. Maybe we can, or you can also have a 2, 1. Let's just have 2, 1 here. So we have 2, 1 as our point. So that point, the test point will be 2, 1. So we are going to evaluate this inequality here at this point. So when x is equal to 2, we have 2 plus y is 1 less than or equal to 6. So is 3 less than or equal to 6? The answer is yes. Next, we consider y less than 2x. So for y less than 2x, our y is 1. So 1 less than or equal to 2, and then our x is 2. So is 1 less than or equal to 4? It's yes. So both of the inequalities are satisfied. So therefore, we say that region 2 is the feasible region. So now that we have identified region 2 as our feasible region, we'll go ahead and identify the rest of the critical points. So this is the point, this is the x-intercept, that is actually the point 6, 0. This is the point 0, 0. So our critical points are the vertices of our feasible region. So the feasible region is this given region here. So let us identify the vertices. The vertices are the points 0, 0, 2, 4, and 6, 0. Then after that, we're going to evaluate our function here. We are going to evaluate this given function here and see which one will give us the maximum value. So to maximize this, let us just evaluate it at the critical points. So now let us just evaluate this function here at this critical points, at each of those critical points. So we have c at 0, 0. So that is just 25 times 0 plus 15 times 0, which is equal to 0. And then next c of 2, 4, we have 25 times 2 plus 15 times 4. 25 times 2 is 50. 15 plus times 4 is 60. That gives us 110. The next is evaluate c at 6, 0. c at 6, 0, 25 times 6 plus 15 times 0. Now, 25 times 6 is 150. Therefore, the highest value here is 150. So this one, the point 60 gives us the maximum value. So this is the maximum value. And this maximum value here is achieved at the point 60. Next, let us solve the following problems graphically. We want to maximize the function f of xy equal to 15x plus 9y, subject to the following constraints here. We will solve this, or we're able to solve this by first identifying the feasible region. And to identify the feasible region, we will first have to graph the line x plus y equals 4, the line x equals 10, the line y equals 20, and this last constraint here means it is on the first quadrant. first quadrant because y has to be greater than 0 and x has to be greater than 0. Now let us graph these constraints here on the first quadrant. So let us begin by graphing these two equations here, x equals 10 and y is equal to 20. So for instance, when y is 20, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Suppose we do increments of 2 here. This would be our graph for the line y is equal to 20. And then for x is equal to 10, let's consider a different color here. 2, 4, 6, 8, 10. So this is this line here. That is for the line x is equal to 10. Then we will graph the line x plus y equals 4. To do that, we can get a representative point. So we have x and y. We get the x-intercepts. When x is 0, y is 4. When y is 0, x is equal to 4. So we have, this is increments of 2. So if x is 0, y is 4. It is this point here. Let's use a different color. It is this point here. And then when x is equal to 4, y is 0. It is this point here. So we are considering this line here. Okay, so now it is just on the first quadrant. So therefore, we are going to get the different regions. So let's identify the different possible feasible region. We can have this one here, region 1. This is your region 2, region 3, region 4, and region 5. These are all the different regions or the different possible feasible region. So our next goal is to identify which of these 5 regions here is the feasible region. We'll do that by getting a representative point. Now this one is a little bit easier because we have these constraints here which we could easily identify. We know that x has to be less than 10. So if x has to be less than 10, the regions that satisfies that are the regions 1, 2, and 3. So therefore x and 4 will immediately get eliminated. So we were not going to consider that anymore. Let's just use a red one here. So this one is no longer a feasible region. So we only have these 3 as the possible region. Now also we have y has to be less than or equal to 20. So among these 3 regions here, which one is less than 20? Less than 20 are 1 and 2. So this region 3 is also not a feasible region. So we're just going to test 2 and 1 as our feasible region. So let's look at region. So let's look at region 1. So our region 1, what would be your test point? You could have 0, 0 as your test point because we have equality symbols here. If you want a number in between, let's say for instance, you can have 1, 1 because each of these lines here are 2. So you could also have 1, 1. So our test point, let's just do 1, 1. So 1, 1, and then we will just have to try and see if that is satisfied by this inequality here. So we have 1 plus 1. Is that less than 4? The answer is yes. Now that is the only inequality that we're going to test because we already have tested these 2 here that has to be satisfied by those regions. So therefore, from here we see that region 1 is a feasible region. Now, just for the sake of illustration, we look at region 2 and we will verify that this is not the feasible region. So if you get the test point, a test point for region 2, let's say for instance we have we get here a point. This point here, this is 2, 2, 4. So we have 4, 6. Consider the point 4, 6. Then you plug it in here. So if x is equal to 4 plus 6, is that less than 4? So we know that 4 plus 6 is 10, and that is not less than 4. So therefore, this one is not a, region 2 is not a feasible region. So we have verified that between 1 and 2, region 1 is the feasible region. So now that we have identified region 1 as our feasible region, the next step is to identify the critical values. The critical values are the endpoints of this feasible region here. So our critical values, or the critical points, or points, so not the values, the critical points, will be, the critical points are the points 0, 0. So this point here, this is the point 0, 0. And this point here is the point, so every unit here is 2. So you have 2, 4. So that is 0, 4. X coordinate is 0, y is 4. And here, this is also 2 points, so 2, 4. So this is the ordered pair 4, 0. So these are all our critical values. So next is to identify or evaluate this function here at each of the critical points. So we have f of xy equal to 15x plus 9y. 15x plus 9y. So we will evaluate f at 0, 0. We have 15 times 0 plus 9 times 0. 0 plus 0 is equal to 0. Next, let's evaluate 15 f of xy at the point 0, 4. So if you have 15 times 0 plus 9 times 4. 15 times 0 is 0. 9 times 4 is 36. So therefore, the value here is 36. Then, lastly, evaluate f at 4, 0. So you have 15 times 4 plus 9 times 0. 15 times 4 is equal to 60. So we have 60 plus 0, that is equal to 60. Now we have seen here that the maximum value, because we want to maximize, yeah, if it says minimize, so that's the smallest value. Since we want to maximize here, we want to find the largest value. So the maximum value here is equal to 60. And it is achieved at the point 4, 0.